Good day, everyone. So for today's experiment, we will discuss experiment 1, measurement. The objective of this experiment is to acquire skills in using the ruler and a vernier caliper, and to determine the mass density of some solid materials. From our previous discussion, measurement is the process of comparing the unknown attribute of the object to a standard value. This attribute can be length, like this, okay, so that is the length, and we will compare it to the standard scale, which is centimeter, and we use a tool, which is our ruler. And another attribute of the unknown material that can be measured is mass. We use a weighing scale. Or a temperature, we use thermometer. Or the time, we use a stopwatch or a clock. Beginner in physics course, a student should acquire skills in accurate measurement at the very start, because a lot of measurements will be done during our laboratory activities, and so for this reason, some of the fundamental techniques of having accuracy and measurement should become a habit. So the first thing you have to remember in measuring or using a ruler or meter stick, when measurements are being made with a meter stick or a ruler, the scale, which is this is what we call the scale, should be placed edgewise. So this is edgewise on the object that is being measured, so that the graduated, so that is the line, so the graduated is what we call the lines of the meter stick or a ruler comes in contact with the object to be measured. Next, so the eye of the observer, or the one who is measuring the object using the ruler, should always be placed at the same level or in line with the point of scale which is to be read. In some cases, since some of the ruler are worn out, or some of the meters are worn out like this, the edge are worn out, or the scale cannot be read anymore, so it is best to begin the measurement by sliding the ruler over an even number of the centimeters. So for example, you might start from, if this is worn out or you cannot read the scale here anymore, you can either start at 1 or 2. So it's up to you, but make it sure that you can read clearly the scales or the lines of your ruler or your meter stick, unlike this one, in which if you will start at 0, so definitely your measurement will be not accurate anymore, because the edge of the ruler or the meter stick is already worn out. And regardless of the measuring instrument you use, the reading must be estimated always to the nearest tenth of the smallest scale division. So for example, this one, if we will read this one, so this is 1 centimeter, 2 centimeter, and this is 3 centimeter, but the object just reached into this fourth line, so that is 2.1, 2.2, 2.3, 2.4 centimeter. So therefore, that the 0.4 is what we call the 10th position. Definitely, we cannot read the 100 or 1000 or 10,000 position based on our instrument, okay, because that is the limitation of a ruler or our meter stick. There are some cases in which that the edge of the object is between lines, between the two lines. So for example, this is 3, 3.1, 3.2, 3.3, 3.4. So the edge of the object is between 3.4 to 3.5. You might assume that the length of that object is 3.45. You might attempt to read the 100 position. So because of this limitation of a ruler on our meter stick, our measurement to different objects is not really accurate. That's why this man, Pierre Vernier, invented the Vernier Caliper. So the Vernier Caliper is a tool used to measure the length, radius, or the depth of a certain object accurately. So what are the parts of a Vernier Caliper? As you can see, there are 2 scales for Vernier Caliper. This one here, these are the what we call the main scale, and this one is the vernier scale. The vernier scale is movable, so it's either you can move it to the right or to the left based on the length or the how big is your object. The Vernier Caliper actually originated in China during the Qin Dynasty, but there are only main scale in Vernier Caliper in Qin Dynasty and there is no vernier scale. Then the secondary scale invented in 1631 by Pierre Vernier, which is a French mathematician. So the importance of second scale is to measure the length, radius, or the depth of a certain object accurately. So, what are the parts of a vernier caliper? We know that this is the vernier scale. This one is the main scale. This outer jaw or the lower jaw, if we are measuring the outside measurement, just like this is the outside measurement of the cylinder. And the inner jaw, we use it if we are measuring the inside measurement of the object, just like this. So, we are measuring the inside diameter of this object. This one, if once you already place the object in the vernier caliper, you can lock the vernier caliper so that the vernier scale will not move anymore. So that is the lock. And this one is the thumb screw, then this is the depth rod. There are also digital vernier calipers now available in the market, but in this experiment, we will read the readings in the vernier caliper manually. So, how to read a vernier caliper setting? So, first, in step 1, we have to determine first the least count of the main scale. So, how to determine the least count of the main scale? So, look at here. So, since we are going to use an SI unit, so we will look first on the cm here. So, that will be your scale on this main scale. Since that is in cm, so we have to read each this one. So for example, this one is 1. So that is 1 cm, 2 cm, 3 cm, 4 cm, and so on. So that is the main scale. How about the lines in between 0 to 1, 1 to 2, and so on? This between line, how will you read them? Okay? So this one, this first line here, is 0.1 centimeter since there are 10 lines from 0 going to 1. So that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 lines after 0 going to 1. So each line is 0.1 centimeter. So this one, if this is 0.1, this one is 0.2 cm. So from 0 to this line, that is 0.2 cm. From 0 to this line, that is 0.3 cm, and so on. What if the lines will be here? Okay, or the measurement of the object is until here to this line. So that will be 1.1 centimeter. So that is the measurement from 0 going to this point. Okay, so that is 1.1 cm. So here, the distance from 0 to this line is 1.2 cm. From 0 to this line is 1.3 cm, and so on. If the object measurement is until here, it will be 2.1 cm. So it will be here. Then here will be 2.2 cm, centimeter, 2.3 centimeter, and so on. So that is how will you read the main scale. The second one is we have to determine the least count of the vernier scale. So this is our vernier scale, this is our main scale. So let's focus first on the vernier scale. So each line of the vernier scale, so each line of that in the vernier scale is equivalent to 0.05 millimeter. This is the least count of the vernier scale. So it means for this one after 0, this line is 0.05 millimeter. For this line, so the distance from 0 to 1, so this line is 0.10 millimeter. For this line, so that is 0.15 millimeter. So that is the distance always from 0 to the respected line. And the unit here is millimeter. But since our main scale is in centimeter, so we have to convert the millimeter into centimeter. And remember, 0.05 millimeter is equivalent to 0.005 centimeter. For 0.10 millimeter, it is equivalent to 0.01 centimeter. For 0.15 millimeter, it is equivalent to 0.015 centimeter. If you will not remember this conversion, you can compute this by what we have learned from our lecture. So for example, for the 0.05 millimeter, so that is 0.05 millimeter, we will convert it to centimeter. So first, we will convert millimeter first to meter. So we know that 1 meter is equivalent to 1000 millimeter. So from millimeter here, there is a millimeter in the numerator and there is a millimeter in the denominator. We will put it like this so that we can cancel out. Since this in meter and we have to convert it again to centimeter, and we know that 1 meter is equal to 100 cm. Since the meter is in the numerator, so my crossbar here, the meter will be now in the denominator. So 1 meter is equal to 100 centimeter. And we can now cancel out the meter here. So that will be, and the unit that is left in this computation is centimeter. So we will now convert that 0.5 millimeter to centimeter. So we will multiply all the values that is on the numerator divided by the product of the denominator. So 0.05 times 1 times 100 divided by the 1000 is equivalent to 0.005 centimeter. Or if you will express this into scientific notation, we can have 5 times 10 raised to negative 3 to the power of negative 3 centimeter. So here, for step 3, read the main scale mark just before the 0 mark of the vernier scale. So this is now the main scale reading. So for example, we have an object here. So this is the 0 mark in the vernier scale, and this is the line just before the 0 mark in the vernier scale. So it means the reading here is 2.5 centimeter. That is the reading in the main scale. Now for the vernier scale, this might be tricky for the vernier scale. So this is the step. So you have to observe and you have to ask this to yourself. So is the main scale mark, so this is the main scale mark, this one, is exactly in line with the vernier scale 0 mark. So are they exactly or coincide to each other? If your answer is yes, then the 2.5 centimeter is your final measurement or reading. Okay? So if your answer is yes, so if they are in line, exactly in line to each other, so the 2.5 centimeter is your final reading. But if your answer is no, then we have to proceed to step 5 on how to read the vernier scale. So in this case, the 0 mark here is not exactly coincide or in line with the main scale here, which is the 2.5 scale. So therefore, we have to proceed to step 5. So for step 5, what you're just going to do is you have to find, so look on the vernier scale. So for step 5, we have to locate the vernier scale division that is exactly in line with the main scale mark. So first, look on the vernier scale here. Then, from 0, you have to find the first mark that is exactly in line with the mark above in the main scale. So here, for example, this is the 0 mark. Definitely, there is no mark above that is exactly in line with it. This 0.05 mark is not exactly in line with this main scale mark here. Also in this 1 mark, this is also not exactly. This is almost exact but not really. Okay, based on my observation, this is the exact mark that is coincide to the mark in the main scale. Okay, so hopefully that is clear to you. So again, for step 5, you will find the first line, the line in the vernier caliper that coincide or that is exactly in line with the mark on the main scale. Okay, so, and the importance here, once you determine the line in the Vernier scale, you will determine what will be the reading of that based on what we have learned on Vernier reading a while ago. So, that one, I will mark it like that. So, a while ago, we know that each line of this Vernier caliper is 0.05 millimeter. So, what will be the reading of this? So, here, 0.05 millimeter, 0.10 millimeter, 0.15 millimeter, this is 0.20 millimeter, and this one is 0.25 millimeter. So that is the reading of our Vernier scale. Or you can also use this next technique, because this next technique will be very useful if the scales are too many to count, okay? Too many to do this, okay? So this is the method 1. So you will count the equivalent of that of each scale. So you can use this second method, for example. Okay, that is the marks that coincide to each other. So you have to count the lines from 0. Okay, so 0 is not included. From 0 to the mark that coincide, or to the mark that is exactly in line to each other. So from here, 0 is not included. So 1, 2, 3, 4, 5. So that is the number of lines from 0 going to the lines that is exactly in line to each other. Next, you will multiply it to the least count of the Vernier scale. So in our case, the least count is 0.05 millimeter. Okay? So 5 times 0.05 millimeter is now what we call the Vernier scale reading. So that is 0.25 millimeter. Remember, since our reading in the Vernier scale is in millimeter, we have to convert it again to centimeter. So we are just going to do what we have done a while ago. So we will convert it using the crossbar if this method will be easy for you. So that is 0.25 millimeter is just equal to 0.025 centimeter, or 2.5 times 10 raised to the power of -2 centimeter. Now we will go to the last step. For the last step, the measurement taken is recorded as the sum of the main scale and the Vernier scale. So again, if there is a reading for the Vernier scale, the main scale is the final reading. But in our example, there is also a Vernier scale reading. So let's review. The main scale reading is 2.5 centimeter. So that is the main scale reading. And the Vernier scale reading here, based on this, is 0.025 centimeter. And to get the dimension of the object, we will get the sum. So we will just add the 2, and the answer will be 2.525 centimeter. So after we learn how to read the Vernier caliper, let's proceed now to our experiment. Again, the second objective of this experiment is to determine the mass density of the solid materials. So we will have the formula for the mass density. Remember, mass density is mass divided by volume. In symbol, that is rho is equal to m, which is the mass, divided by v is equal to volume, and the rho is equal to mass density. The unit that we will use for this experiment is gram per cubic centimeter. So from determining the volume of the object, so our goal here is to determine which of these two measuring tools will give us an accurate result. So first, we have, for example, this is the object that we're going to measure. First, we have to measure it using the ruler. Second, we have to measure it using Vernier caliper. Then from our measurement using the ruler, we will compute the mass density. So this is the experimental mass density of the object based on the measurement of the volume using the ruler. Then you will also do this. We will compute also the experimental mass density, but the volume here are based on the measurement using the Vernier caliper. Then from these two experimental mass density value using the ruler and the experimental mass density value using the Vernier caliper, we will now compare them to the accepted mass density of this material. And from this, if we will compare the experimental mass density and the accepted mass density, we will now have the percentage error. We will have the percentage error by comparing the mass density using the ruler to the accepted mass density. We will also have a percentage error by comparing the experimental mass density using the Vernier caliper to the accepted mass density. So the one who has a lesser percentage error, it means it has a value that is very near to the accepted value. And if the percentage error is lesser, therefore we can say the tool that we use in measuring that object is more accurate compared to the other one. The first step in this experiment is we have to get the mass of our different shapes. So here we have different shapes here. So we have the cube, we have the cylinder, we have the sphere, and we have the rectangular block. So we have to get the mass first of each material. And based on the mass density formula, we have to get the volume. So it's just proper that we have to know the formula for getting the volume of each shape. So for the block, it's just the length times width times the height. So for the cube, that is the side cube. For the cylinder, pi over 4 diameter squared times its height. For getting the volume of the sphere, that is pi over 6 diameter cube. You will get the volume in two ways, okay? So first, you will get the dimension of these solid shapes using the ruler, and you will also repeat measuring that using the Vernier caliper. That's why for the table 1, we will get the length times width, the height of the cube using the ruler, and you will also get the same length, same width, and same height using the Vernier caliper. Same with the block, same with the cylinder, and same with the sphere. So we will now answer for table 2 and table 3. So for table 2, we will use all our readings based on the ruler reading. For table 3, we will use the Vernier caliper readings. So first, what you're going to put here for the materials. For the materials, you have to determine what type of metal is used for each solid objects that we use in this experiment. For example, for our cube, based on this, that is aluminum, made of aluminum. For the cylinder, that is made of brass. For our sphere here, that is made of iron. And for our rectangular block, that is made of copper. So that is what you're going to place here. Since our first procedure is to get the mass, so you will just note the mass of each solid here. And based on the formula a while ago, you will place your answer here from your computation for the volume. Now, so we will compute for the experimental mass density here. So the computed mass density is also called as the experimental mass density, and it can be computed as mass divided by volume. So the mass here divided by the volume, that is the computed mass density. Then based on what we have discussed a while ago, we will compare this mass experimental density to the accepted density. The accepted densities are here on the list. So the accepted density for aluminum is 2.7 times 10 raised to power of 3 kilogram per cubic centimeter. Since the units are in kilogram per cubic centimeter, so please convert this to gram per cubic centimeter. So after you determine, you will place the values of the accepted mass density based on the table here. That is, the unit should be in gram per cubic centimeter already. You already converted it here. So you will get the percentage error. The percentage error can be computed as percentage error, or PE, is equal to the computed mass density minus the accepted mass density divided by the accepted mass density. And your answer here, inside here, is always positive because this bar means the absolute. Okay, so whatever the sign of your answer here, make it positive, then times 100. So this will be the percentage error. And you will also do this for table 3 for the Vernier caliper. So here, you will place the volume of the cube, block, cylinder, and sphere based on your measurement using the Vernier caliper. Then, you will compute the mass density again, so that is mass divided by volume. You will compare it to the same accepted mass density values that you have used to table 2, and you will compute the percentage error. After completing page 5, also please complete page 6. Now for the calculation, since there are so many calculations for this experiment, please write your calculation in a separate white bond paper or white paper, then answer the questions 1, 2, 3, and 4.